Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines, burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core. a steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even a quarter of an inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied. Marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Imagine a giant factory where copper and aluminum, like two ancient titans, come together in a single dance of heat. The air here vibrates with precision. Coils spin at a speed that could twist time, and furnaces burn brighter than a sunset over the Sahara. Every hour, this mega complex produces hundreds of heat exchangers, the heart of every air conditioning system, refrigerator, or car. It all begins with the gleam of metal. Ready for a deep dive? Then let's head into the very core of production. To start manufacturing, we need to prepare the materials. Copper tubes are made from high-quality copper, often with internal spirals or microfin structures to improve turbulence and heat transfer. Before further processing, the tubes undergo cleaning and annealing to relieve internal stress. Aluminum fins are cut from aluminum alloys, such as 8006 or 1199, which have excellent thermal conductivity and corrosion resistance. The fins can have various shapes: straight, wavy, perforated, to optimize airflow and heat transfer. At large factories, especially in Asia, the United States, or Europe, where heat exchanger production is large-scale and automated, material preparation is part of the same complex. There are workshops that uncoil large spools of copper or aluminum wire, cut plates and tubes to the required length, surface treat them, and store the semi-finished products under controlled humidity and temperature conditions. In smaller production facilities, or in cases of clear specialization, for example, heat exchangers for aviation or military equipment, the blanks may be supplied already prepared from outside. This helps reduce equipment costs and allows focusing on precise assembly and testing. In a huge workshop, where only the rustle of metal and the precise clicking of mechanisms can be heard, the mystery of creating the heart of a heat exchanger, its core, begins. Thin aluminum fins, like metal scales, light, flexible, but with character, are fed onto the conveyor with millimeter precision. They have a complex geometry, corrugated, with microscopic slits that increase the heat exchange surface area, like a fan catching every breath of air. In parallel, from another line, copper tubes slowly slide down. Short, but very important segments, shiny after cleaning, strong and plastic at the same time. Their diameter is precisely matched to the fins. Each tube must pass through a series of holes in the fins, literally piercing the entire stack, like a thread gathering beads. This is done manually only in experimental production, or in the early stages of development, but in most factories, this stage is fully automated. After stringing, mechanical expansion begins. A unique procedure where special mandrels are inserted into the tubes, or they are pressed from the inside with hydraulics. This expands the copper, and it presses tightly against the holes in the fins. The contact must not just be tight, it must be perfectly tight, because this is the area where heat will be transferred from the hot fluid to the cooling air, or vice versa. Every microcrack is a loss of efficiency. In more complex or critical models, the tubes are also brazed to the fins, either in a furnace or by the induction method. The metal melts only on the surface, merging the aluminum and copper into a single structure. The assembled structure is inserted into a frame. On the sides, strong aluminum or steel supports, top and bottom, collectors that will gather and distribute the heat transfer fluid. This is now the core, which will undergo dozens more checks before it ends up in an air conditioner, car, or server cooler. When the core is assembled, a real test awaits it: brazing. First, the structure is prepared, cleaned of oils and contaminants left during assembly. This is done with special degreasers or washing solutions, because any particle of dirt is a potential enemy of quality connection. Then, a filler metal is applied to the brazing spots, a thin layer of alloy, most often aluminum or copper, which melts before the base metal. And here, the key moment: the furnace. Large, sealed like a vacuum capsule, it slowly swallows the blanks. Inside, an oxygen-free atmosphere, often with nitrogen or argon, to avoid oxidation. The temperature rises gradually to avoid creating stress in the metal. At its maximum, about 1,112 degrees Fahrenheit for aluminum, the filler metal begins to flow, but not boil. It fills the gaps, like liquid gold, penetrates the smallest crevices between the tubes and fins, binding everything together, like lava squeezing mountain rocks into a single block. This process is called diffusion brazing, extremely precise and uniform. The furnace can hold dozens or even hundreds of heat exchangers at a time, so each one undergoes processing under absolutely identical conditions. This guarantees stability, no overheating, no underbrazing, and it's also economically viable. After leaving the furnace, the structures shine like newly forged artifacts. Externally, nothing has changed, but inside, a transformation at the molecular level. This is no longer a set of parts, but a single body capable of withstanding years of operation, temperature changes, impacts, vibrations, and aggressive environments. While the heat exchangers are still hot, they are slowly cooled in a controlled environment. This is not just a technical procedure, it's a hardening ritual. If cooled too quickly, the metal structure will develop microcracks. If slowly, without control, the geometry will be compromised. So, after the fire comes water. After the insane temperature when the solder flowed between the aluminum and copper, the heat exchanger seems to take a breath. It has survived the hottest moment of its life. But ahead lies an equally responsible stage: cleaning, inspection, protection. First, the heat exchanger enters a washing zone. Here, the remnants of flux, the substance that helped the solder flow evenly and tightly, are washed off. If left, it could later cause corrosion or reduce the device's efficiency. Therefore, the part is bathed in special tanks, hot water, neutral solutions, sometimes ultrasonic cleaning, everything to make every millimeter shine with cleanliness. But beauty is not everything. Each heat exchanger is tested for leaks. Imagine air hoses being connected to it, submerging it in water, and applying pressure. Even a tiny bubble means a problem. Either a joint wasn't properly brazed, or a microcrack has formed, and then it's off for reprocessing. But if the water remains calm as a mirror, the product moves on. Strength is also checked by pressure, often higher than what the product will withstand in real conditions. After this, the final cosmetics. Aluminum elements may be anodized. This is an electrochemical process that creates an oxide film on the surface. It makes the material resistant to rust and adds an elegant matte sheen. Sometimes special protective coatings are applied, varnish or polymer paint, which not only adds color, but also protects against aggressive environments. The world is changing, and heat exchangers are changing with it. While classic copper tubes and aluminum fins still serve faithfully, new heroes are appearing on the horizon, with the strange gleam of future technologies. One such breakthrough is aluminum-clad copper tubes. Imagine this: lightweight and corrosion-resistant aluminum. On the outside and inside, a copper heart that conducts heat with incredible efficiency. This combination preserves the key advantages of both metals, minimizing their weaknesses. These tubes, like a perfect union of opposites working in harmony. They are easy to process, lighter than pure copper, cheaper, and yet provide thermal efficiency on par with top-tier solutions. But the brightest future belongs to 3D printing. In sterile laboratories, where printers don't apply ink but molten metal, structures are born that previously existed only in the fantasies of engineers. Here, they don't just copy familiar tubes and fins, they create new geometries, spirals, lattices, organic forms that mimic the microstructures of bones or leaves. They are lighter, more efficient, more compact, and they can be tailored to a specific device or operating condition down to the smallest detail. These printers can work with copper, stainless steel, and eventually, new generation composites. Such products cool processes faster, transfer heat more efficiently in electric vehicles, and last longer in harsh climatic conditions. And all this with fewer resource costs and minimal heat loss. Every year, over 20 million metric tons of copper are mined worldwide. But only 1% of that massive amount makes it into the shape we see every day, as thin pipes that cool our homes, offices, and skyscrapers. This story begins in the giant mines of Chile, where excavators as tall as 5-story buildings dig up the ore from which a gleaming pipe is eventually born. From explosions in quarries to magma in furnaces. From thousands of degrees to surgical precision. How does a piece of mountain rock turn into an air conditioner? We're about to show you the whole journey, step by step. Deep underground, in the deserts of Chile, the steppes of Kazakhstan, and the mountainous regions of Australia, work is buzzing, slow, monotonous, but extremely important. Here, copper ore is extracted, the raw material from which thin, shiny pipes for air conditioners are later born. This process begins far from factory workshops, in giant quarries, where every explosion, every excavator bucket, is a step towards the metal that will cool rooms in skyscrapers and apartments. In Chile, which produces nearly a third of all the world's copper, there are giant open pit mines. For example, the famous Escondida. Here, mining machines as tall as a 5-story building slowly move down the terraces, scooping up rock from which only 1% of copper is extracted. Imagine, to get 1 ton of metal, you need to crush over 100 tons of rock. After extraction, the ore goes to crushers, huge machines that turn rock into pieces the size of a walnut. Then, even smaller, down to sand. This sand goes to flotation plants. There, using water, air, and chemical reagents, copper floats to the surface as foam, which is skimmed off, dried, and sent for smelting. All of this is heavy, energy-intensive work, but without it, there would be no pipes, no air conditioners. From the first blast in the quarry to the thin pipe in an office, the journey takes months, covering thousands of miles. And each stage is a story of its own. Raw ore isn't transported to the factory where copper pipes for air conditioners are made. That would be too bulky and inefficient. Instead, after concentration and primary processing, it's turned into a more concentrated, transportable product. Depending on the supply chain, the factory might smelt the concentrate or mat themselves, producing pure copper if they have melting facilities. Or they might purchase cathode copper in the form of plates and then form blanks for pipes from it. Shiny rectangular plates. These are copper cathodes, weighing up to 200 pounds each. They are stacked on pallets and brought to the factory in incredibly long trucks. This is almost pure copper, over 99.9%, and it will become the heart of future pipes. But first, it will turn into red-hot ingots. Cathodes are removed from pallets and inspected, checking for cracks, oxidation, or dirt. Next, they need to be cut for remelting, as they are incredibly large. The cathodes are placed one after another on a hydraulic table, and a heavy-bladed press descends from above, literally chopping the copper in half. The sound is a dull metallic thud, almost like a gunshot, quick and precise. When more complex shapes or smaller volume are needed, a bandsaw with carbide teeth is used. It slowly but steadily cuts the copper, like wood, only with water cooling, because the metal heats up. If the copper needs to be cut at the melting location, a plasma cutter or an acetylene torch is sometimes used, a stream of burning gas that melts the metal along the cut line. But for cathodes, this is less common. It's too expensive a technology. All operations are usually automated. Cathodes are brought by a crane or forklift, loaded onto a conveyor belt, and everything moves down the line. The cut pieces are immediately fed into the furnace. The operator only ensures that everything moves smoothly and without jams. The cut pieces fall onto a metal roller or chain conveyor. There they lie flat, often in a single layer. If needed, they are separated by special pushers to prevent them from sticking together or getting stuck. This conveyor works slowly but powerfully. The task is to continuously feed copper into the furnace without creating bottlenecks or downtime. After melting, fluxes are added to the molten metal, substances that collect impurities and scale, help keep the copper clean and shiny, and reduce slag formation. The fluxes float to the surface as a dark film, which is scooped up with a mechanical skimmer and discarded. As soon as all the copper has melted and become a uniform, shiny mass, the temperature is equalized and the furnace opens from the bottom or tilts, pouring the metal into casting molds. The molds resemble long, rectangular boxes with thick walls, made of strong steel capable of withstanding intense heat. The furnace is tilted, or a valve is opened, and the hot molten copper begins to flow along a special channel, like a bright orange river of magma. This channel leads to the mold, which stands ready to receive the metal. The mold is cooled by water or air, so the copper entering inside begins to solidify quickly. Immediately after pouring, the mold is often lightly tapped or vibrated a bit. This helps air bubbles and voids escape from the molten metal, ensuring the ingot is strong and without defects. The mold stands on a special platform that sometimes moves or tilts slightly, helping the metal distribute evenly. The hot steam rising above the mold resembles volcanic smoke. Workers in special protective clothing observe the process, ready to intervene if something goes wrong. As soon as the copper in the mold cools and solidifies, the mold is opened and a long, shiny ingot comes out, a large piece of copper, ready for further processing. These ingots can weigh hundreds of pounds and look like metal bars with a smooth, shiny surface. The ingot that came out of the mold first undergoes quality control, checking its weight, shape, and absence of cracks or defects. Then it is heated to a certain temperature to make the copper softer and more pliable for further processing. Next, the ingot enters a large rolling mill, where it is gradually rolled between rollers, stretching and making it thinner. Rolling happens several times to make the ingot longer, thinner, and more uniform in thickness. After rolling, the metal undergoes special forming. It is turned from a flat strip into a cylinder, which is then welded along the seam or blown into a pipe shape. This process is very precise. The diameter and wall thickness are regulated with great accuracy so that the tubes can withstand pressure and don't burst. After forming, the copper tubes are still hot, almost like a freshly baked bun. To prevent them from deforming and to keep their perfect shape, they are cooled quickly. For this, the tubes are passed through long pools of cold water or special cooling baths. Water sprays from different sides, flowing around the metal, and it cools down instantly. Then, the most interesting part begins, checking the dimensions. The tubes pass through special calibrating devices. This can be a set of rings or sensors that measure the pipe. Each ring corresponds to the exact inner or outer diameter. If the tube passes through the ring without problems, the size is normal. If not, an automatic sensor signals, and the operator stops the process. If the pipe meets the standards, it is sent further, for cutting or packaging. If not, it is returned for rework or recycled, to prevent defective products from reaching the customer. After the copper tubes have undergone forming, cooling, and calibration, they proceed to the next important stage, cutting into standard or ordered lengths. This process is very important, as the quality and ease of installing the pipes in air conditioners depend on the accuracy of cutting. The tubes are usually supplied in the form of long straight sections or coiled into bundles. First, they are uncoiled or fed along a conveyor to a special automatic cutting machine. This machine is equipped with a powerful cutting disc or saw that rotates at high speed. The operator sets the precise parameters for the cutting length, for example, 10 feet. The tube is fed forward, and the machine precisely cuts off a piece of the required length. The moment the cutting disc touches the copper, sparks fly, and the metal almost hisses and smoothly separates into two parts. The movement of the disc is very fast and smooth, so the cut is even and clean, without burrs or cracks. The finished tube sections are packaged into bundles or boxes, often wrapped with tape for easy transport. Each package is marked, indicating the tube dimensions, wall thickness, and production date. Every year, the world produces over hundreds of millions of artillery shells, complex and precise items that play a key role in modern armed forces. From the smallest shells to heavy 6-inch casings, each one goes through a complex path, from metal scrap to a powerful munition capable of changing the course of a battle. Huge factories work continuously, using the latest technologies and high-precision equipment to provide armies worldwide with reliable and effective weapons. In this video, we will delve into the process of manufacturing artillery shells. From metal processing and forming the casings to filling with explosives and testing the finished product. Get ready to see how millions of tiny details turn into a formidable weapon, and understand why this is so important for the security and defense capabilities of countries. Don't miss it. It will be spectacular and extremely interesting. The production of artillery shells begins with the selection and preparation of the metallic material. The basis for most shells is high-quality steel, which provides the necessary strength, heat resistance, and accuracy. Metal for blanks is usually supplied in the form of large rolls or sheets, with thickness ranging from a few tenths of an inch to several inches, depending on the caliber of the shell. In the United States, annual steel production is approximately 87 million tons, or about 96 billion pounds. From this enormous quantity, a certain portion goes to the defense industry, where the metal undergoes strict quality control and certification. For example, special alloy steel is used for artillery shells, which has increased strength and corrosion resistance. Blanks for shells are made at steel mills, where the metal is melted in large furnaces at temperatures exceeding 2,700 degrees Fahrenheit. After this, the molten metal is poured into molds, resulting in large plates or rectangular blocks. Then these plates are rolled on rolling mills, reducing the thickness to the required parameters, 2 inches and less. Rolling mills can be either hot or cold, depending on the processing stage. Hot rolled sheets have lower accuracy, but are easily formed, while cold rolled sheets are ideal for parts requiring high precision and a smooth surface finish. Next, the metal sheets or rolls are transported to munitions plants. Here, using equipment, the shell casings are cut from the blanks, tubular or cylindrical, depending on the type of munition. In 1 hour, a modern facility can process hundreds of thousands of pounds of metal, transforming it into hundreds of finished casings. To understand the scale, in 2022, the United States manufactured over 10 million artillery shells of various calibers. Considering that one shell casing weighs about 100 pounds, producing this quantity required over 1 billion pounds of special steel. Blanks arrive at the munitions plant, where their transformation into actual shells begins. Heavy spools of steel or other alloy, weighing several tons and stretching hundreds of feet long, are placed on special uncoiling platforms. These setups unwind the roll like a giant spool, feeding the steel strip further down the line. In the next stage, high-precision guillotine shears, or rotary disc cutters, are used to cut sheets or discs of precisely specified length and width from the roll. For shells of different calibers, from less than an inch to 6 inches, different sized blanks are needed, so the computer numerical control system adjusts the cutting parameters to the required standard. Next, the blanks are heated in industrial furnaces to a temperature of approximately 2,000 degrees Fahrenheit. The metal becomes plastic, like clay. It is transferred to hydraulic presses, where, under pressure of hundreds of tons, the future shells are given their initial shape, an elongated cylinder with a pointed end. After the metal blanks have undergone initial forming, usually by deep drawing or hot stamping, they are still far from ideal. The blanks come out slightly deformed, with excess length, an uneven edge, and micro bends. Therefore, the next stage is calibration and trimming. The hot part cools in special baths or under a stream of air, so the steel sets in its new shape. Then the shell is fed to a trimming machine. Rotating blades or milling cutters cut off the excess length. For example, for a large artillery shell, the typical casing length is 15.6 inches. This is accuracy not by eye, but to the thousandth of an inch. After this, the part passes through a calibrating unit. This is either crimping rolls or boring systems with precision micrometers. The casing diameter must match the standard plus or minus 0.001 inch. Otherwise, the shell will either not enter the gun's chamber or will get stuck. At the output, we have a part ready for further processing, with clear geometry and parameters. The blanks slowly move inside the computer numerical control machines, massive machines with gleaming tools rotating at speeds up to 15,000 revolutions per minute. Sharp milling cutters, resembling miniature circular saws, cut off excess metal with surgical precision, as if engraving the steel cylinder. Under the automatic aim, the location for the rotating band, a narrow groove that holds a copper ring, thanks to which the shell moves along the rifling of the gun's barrel. Then, threading for the fuse. The supply of coolant is accompanied by hissing and steam, sparks, steel, fog. Every turn of the tool transforms a formless blank into a high-precision shell. After milling, the shell casings are sent to the heat treatment stage. And this is, without exaggeration, a fiery forge of high technology. The blanks are submerged in furnaces where the temperature reaches over 1,600 degrees Fahrenheit. In a dark hall filled with the orange glow of the metal, giant furnaces heat the casings to a state where the steel becomes more flexible, loses stress, and acquires the necessary strength. After heating, rapid cooling. This is either an oil bath, streams of air, or water quenching. The choice depends on the type of alloy. The process is called hardening, and it's what transforms the shell casing from a simple blank into steel capable of withstanding the immense stress during firing. Next, grinding. Each casing passes through machines that, with a screeching sound, remove microns of remaining scale, irregularities, and excess material buildup. Streams of coolant create a mist, and the air smells of metal and machine oil. Workers in safety glasses carefully monitor each casing so as not to miss any micro cracks or deformations. After grinding, it's time to move on to the most important part, creating the explosive filling. Before this, the casings go through a degreasing and inspection stage again. Not a speck of dust or a drop of oil should remain inside, so as not to affect the stability of the explosive material. A component is installed in the rear part of the shell through which the charge will later be introduced, or it is sealed immediately if the design requires it. If it's a high explosive shell, the casing is filled with explosive material, usually TNT, octol, or a mixture like Composition B. The process can be casting, where molten explosive is poured into the casing, or pressing. This is an extremely delicate and controlled process. Everything happens automatically, with remote control and under the supervision of specialists in armored cabins. A socket for the fuse or the fuse itself is inserted into the nose part of the shell, either immediately before use or during manufacturing. Everything is sealed to prevent moisture from entering. In the final stage of manufacturing, artillery shells enter the paint booths, large rooms with exhaust fans, filters, and automated sprayers. Here, the shell casings are covered with a special paint that not only marks the type of munition, but also protects the metal from corrosion during storage or transport. The color matters. Yellow, for high explosive fragmentation, green, for smoke, black, for armor piercing, and blue often indicates training rounds. The paint is applied evenly, in a thin layer, usually in several passes, so as not to exceed the permissible weight of the shell. After drying, marking follows. Caliber, shell type, serial number, batch number, production date. This is done with a stencil or using an industrial printer. Every detail matters. Military personnel need to quickly identify exactly what they have in front of them, under what conditions it can be used, and from which batch it came. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us, and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning it up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher, and while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. 1 barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet, and that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Imagine a factory the size of 15 football fields where machines run non-stop, and every hour, enough pipe comes off the conveyor belt to wrap around Manhattan twice a day. This giant complex is the heart of infrastructure, supplying pipes for high-speed railways, city water mains, and many other critical projects. It all starts with a white powder. Interesting, right? Then let's keep going. It all begins with the raw material, polyvinyl chloride resin, or PVC resin, delivered to the factory by the truckload, literally tons of it. Every day, the plant consumes over 500 tons of this white powder. But this is just the base. Stabilizers, lubricants, colorants, and other special additives are added to give the future pipes strength, flexibility, and resistance to external factors. All components are precisely weighed and thoroughly mixed in high-speed mixers. This is crucial because even the slightest error in dosage can affect the quality of the final product. Thanks to modern automation systems, each batch of mixture comes out identical down to the last gram, like a favorite recipe repeated with meticulous precision. Interestingly, the factory's silos can hold over 2,000 tons of raw material. That's roughly equivalent to 800 truckloads of sand. Such a reserve allows production to run continuously, ensuring stability and high productivity. So, this first stage is the foundation upon which all the subsequent quality and durability of the plastic pipes are built. The finished mixture is fed into huge twin-screw extruders, machines the length of a school bus. Inside these giants, the mixture is heated to a scorching 660 degrees Fahrenheit, transforming from a dry powder into a thick plastic mass ready for shaping. This process is very important, because it's here that the material acquires a uniform structure, which determines the strength and longevity of the future pipes. The extruders operate continuously, feeding the mixture at speeds up to 30 feet per minute. That's roughly the speed of a slow walker, but with incredible metallic precision and stability. Thanks to this speed and control, the factory can produce thousands of feet of pipe daily without sacrificing quality. This stage is the true heart of production, where science and technology merge in a perfect dance of molten plastic. Next, the molten polyvinyl chloride is pushed through special molds, calibrators or sizing sleeves, which give the pipes their precise diameter and required wall thickness. These huge molds can create pipes with diameters up to 4 feet, ranging from small water pipes to true giants for sewer systems. Each pipe comes out perfect in size and shape. The length of the finished pipes can reach up to 40 feet, which is about the length of a double-decker bus. As soon as the molten polyvinyl chloride passes through the calibrator and takes the shape of a pipe, the next critically important stage begins: cooling. This stage takes place in long baths filled with cold water, where the pipe's temperature rapidly drops from approximately 660 degrees Fahrenheit down to room temperature, about 68 degrees Fahrenheit. If the pipe cools too quickly, it might deform or lose strength. If cooling is too slow, production will slow down, and quality might suffer due to uneven solidification of the material. That's precisely why factories use specially designed baths that ensure the ideal temperature regime. These baths can contain over 13,000 gallons of ice-cold water, equivalent to about 20 large home swimming pools. The water circulates and is maintained at a constantly low temperature to effectively draw heat away from the pipe. The time a pipe spends in the bath depends on its diameter and wall thickness, but it usually ranges from a few minutes to half an hour. During this time, the plastic hardens and gains the strength needed for further processing and use. After cooling, the pipe emerges from the bath and passes through a system of rollers that maintain its shape and guide it further down the production line. This stage ensures that the pipe remains straight and doesn't deform under its own weight. Thanks to such thorough cooling, the finished plastic pipes possess high mechanical strength, impact resistance, and durability, allowing them to serve for decades in various applications, from water supply to sewage systems and even industrial systems. So, a cold shower isn't just good for people. After the pipe has passed the cooling stage and gained the necessary strength, it's time for one of the most important and yet most delicate processes: cutting and marking. This is the final touch that transforms the long plastic ribbon into a finished product, ready for shipment to customers worldwide. First, the pipe moves onto a special cutting line, where automatic cutters precisely and quickly cut it to the required length. This process is fully automated and controlled by computers, ensuring that each pipe perfectly meets the specified standards. The line speed is impressive, reaching up to 30 pipes per minute. That's roughly one pipe every 2 seconds. For comparison, that's the speed of a professional barista during peak hours, making coffee for a crowd of customers. Cutting is performed using high-precision equipment that employs disc or bandsaws with diamond coating. This ensures the pipes are cut without burrs or irregularities, which is very important for future use, as even the slightest unevenness can cause leaks or damage. After cutting, each pipe passes through a marking station. Here, all necessary information is applied to the surface: the manufacturer's logo, technical specifications such as diameter, wall thickness, pressure class, as well as the production date and other important data. Marking is done using laser printing, a modern, non-contact method that ensures extraordinary precision and durability of the applied information. The laser burns symbols onto the pipe surface with millimeter accuracy without damaging the material or affecting its strength. This is crucial because the marking must remain clear and legible throughout the pipe's service life, even under harsh operating conditions, underground, in water, or when exposed to chemicals. After marking, the pipes undergo a final visual and automatic inspection. High-resolution cameras scan the surface, checking the quality of the cut and the applied text. If the system detects any defects, the pipe is rejected and sent for reprocessing or disposal. After passing all stages of cutting, marking, and inspection, the pipes are carefully stacked onto pallets or special carts. They are ready for packaging and shipment to customers worldwide, from large construction projects to private orders. Huge conveyor belts smoothly carry the pipes to automatic manipulators, large robots with gentle hands that operate with amazing care. Each pipe, up to 40 feet long, is picked up like a fragile treasure and carefully placed onto a pre-prepared pallet. The robots maintain perfect order. Pipes are stacked one on top of the other, forming strong, even layers. Each layer is aligned with inch precision to prevent shifting and ensure stability during transport. Meanwhile, operators monitor the process, carefully ensuring that no pipe is damaged or displaced. Once the pallet is filled, it's wrapped with strong strapping or film, protecting the pipes from dust, moisture, and mechanical damage. Then, the pallets are carefully moved using forklifts to warehouse areas, where they await shipment. Polyvinyl chloride was first synthesized back in 1835 in Germany, but its widespread use in pipe manufacturing only began in the 1930s, when a German company developed an effective technology for producing the material. In the United States, these pipes gained popularity due to their lightness and durability. Interestingly, the colors of the pipes are not random. Orange or gray colors are used for protection against solar radiation, which significantly extends their service life. Did you know that? Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting